The next item on the main menu is Time Temperature Superposition or TTS. It is a powerful tool which we can use to predict a material's rheological behavior at a different time or shear rate by using its behavior at a different temperature and vice versa. For example, we can decrease a material's shear stress either by increasing the temperature or by decreasing the shear rate. Thus, the effect of shear rate can be predicted if we know the effect of temperature provided we scale these effects properly. In TTS, we use shift factors to shift or scale the time or shear rate to superpose viscosity or relaxation modulus data obtained at different temperatures and create a master curve. After we create the master curve, we can also analyze how the shift factors depend on temperature and which model best describes this dependence. It is important to note that TTS is not applicable to all materials. For TTS to work, the material has to be rheologically simple. That is, all its relaxation modes must have the same temperature dependence. In fact, the applicability of TTS can be used to investigate whether a material is rheologically simple or not. On the main menu, as we press the Time Temperature Superposition button, it takes us to the TTS submenu. Here we see there are two options, TTS viscosity and TTS relaxation modulus. In TTS viscosity, we use our viscosity versus shear rate data obtained at different temperature for the superposition, whereas in TTS relaxation modulus, we use relaxation modulus versus time. Let us now try the first option, TTS viscosity. We are now on the TTS viscosity screen. Here we will enter our experimental data points one by one manually. Each data point consists of three variables, temperature, shear rate, and viscosity. When we enter our TTS data, we can group our data points by temperature, and we will call each group a temperature series. That is, we will first enter the shear rate versus viscosity data for one temperature series, and then we will move to the next series, and so on. For example, we will enter 4 temperature series data for our TTS viscosity analysis. We have finished entering 44 data points consisting of 4 temperature series, 180 degrees, 220 degrees, 260 degrees, and 300 degrees Celsius. To look at the data we just entered, we can press Plot Data Series button and it will show the plots for these 4 temperature series. Before we generate the master curve, we have to select a reference temperature. We select it from the drop-down list. Let us choose 260 degrees as our reference temperature. We are now ready for the master curve. We press the button Create Master Curve and we get the message that the master curve is now created. We also get the shift factors AT versus the 4 temperatures. To see the master curve, we press the Plot Master Curve button. We can see that the 4 temperature data series merged nicely onto a single master curve. It also tells us the material was rheologically simple. Next, we try to fit the shift factors AT as a function of temperature using either the Arrhenius model or the WLF model. We try Arrhenius first. As we press Fit to Arrhenius, it gives us the activation energy EA and the relative error of the fit. The relative error in this case is quite large. We also check the model fitting graphically by pressing the Plot Fitted Model button, and it is clear that the fit is not really good and the Arrhenius model may not be our right model. So we choose the WLF model to see how that fits the shift factors. As we press Fit to WLF, it gives us a much better fit in terms of relative error. We also look at the plot and find that the WLF model nicely fitted the shift factors. So we will go with the WLF model to describe the temperature dependence of the shift factors of our material, and our model parameters are C1 equal to 6.9 and C2 equal to 167 Kelvin, corresponding to a reference temperature of 260 degrees Celsius. The second option on the TTS submenu is TTS Stress Relaxation. Using this tool, we can superpose relaxation modulus versus time data measured at different temperatures by shifting them on the time axis to create a master curve. On the TTS Stress Relaxation Modulus screen, we will load our experimental data points by entering temperature, time, and the relaxation modulus. Similar to TTS viscosity, we will group our data points by temperature and we will call each group a temperature series. We have finished entering 46 data points consisting of 3 temperature series, 160 degrees, 200 degrees and 240 degrees Celsius. To look at the data we just entered, we press Plot Data Series button and it will show the plots for these 3 temperature series. Before we generate the master curve, we have to select a reference temperature. Let us select 160 degrees from the drop-down list. Then we press Create Master Curve and get the message that the master curve is created. It also gives us the shift factors AT versus the 3 temperatures. To see the master curve, we press the Plot Master Curve button. We can see that our 3 temperature data series merged nicely to form a single master curve. It also tells us that the material was rheologically simple. Next, we try to fit the shift factors AT as a function of temperature. As we press Fit to Arrhenius, it gives us an activation energy EA of 74.98 kJ per mole. We can see that the relative error is quite small. We also check the model fitting graphically by pressing the Plot Fitted Model button and find that the fit is quite good. So we will accept this TTS analysis and will go with the Arrhenius model to describe the temperature dependence of the relaxation modulus of our material.